Hi guys, uh, in today's session we will discuss about how to design a single port RAM. So we will write a code in Verilog and we will also verify the behavior of that code by writing a test bench in Verilog. Single port RAM. So as we all know, RAM is a volatile memory, right? So first of all we need to understand the block level diagram, and after that we'll go for coding part. Right, so let's say that is your RAM and it may have some signals. So let's say this signal is for clock, this signal is for reset, this signal is for enable, right? Let's say output enable, or you can say it is just for enable, and this signal will tell when the output is available. So let's the name is output enable. After that reset we have done, clock we have done, address ADDR. After address, next one is let's say data in, right? And one more signal should be there. That signal name will be data out, right? So first of all we need to understand that this block is the RAM, this is the chip of RAM, this is just an integrated circuit, an IC, right? It have some signals like clock, reset, output enable, address, data in, data out, and enable signal, right? So what is the difference between this output enable and enable is enable will enable the RAM, the whole chip, while output enable will be high when the output is available at the output port, at the data out, right? One more signal should be there because we need to tell that what operation we are going to perform, whether it is read operation or write operation. So let's say one more signal name is write underscore read. So first of all we need to develop the design of that RAM, right? And this signal will be part of your IOs. Okay, so let's go for GBeam. So first of all module, let's say module name is RAM and module. Here you need to mention all the IOs as we discussed in the clock diagram, like clock. After that let's say reset n instead of reset, so n will tell that it is active low reset. After that enable, after that address, after address write underscore read, and after that data in, after that data out, and output enable. So we have done with all the IOs. Now we need to tell that out of these signal which one are input and which one are output, and we may also need some local signals, local variables or resistors, and also we need to tell their dimensions, right? So let's say input, your input will be like clock, reset n, enable, and write underscore read. So they will be your single bit inputs. After that, input, here let's say I am writing 7 down to 0 and data in. So what it will do, it can deals with only 1 byte data, because 8-bit equal to 1 byte, right? So we want to make some generic code, so we'll see how we can make. So for now I am just commenting this line. So we can write input, let's say, okay, let me data width -1 down to 0, that is data in. We'll see later what is the mean of tick data width, right? After that, next input is address. So let's write tick address width -1 down to 0 address. After that, we need to declare output. So just declare output reg. After that, tick data width -1 down to 0, that will be your data underscore out. After that, one more signal is there, that is output enable. It's up to you whether you want to take this signal as a reg or not for output enable, right? Okay, so now let me tell you what is the mean of tick width, tick address width or tick data width, right? So let me create one more file, defines.b, right? So in this file we will see that why we declare like that, tick width, tick address width or something. So tick define address width and let's say I'm writing 6. After that I am writing tick define data width, let's say 32-bit data. After that, tick define depth. We will also use tick depth, right? That is 64. So what is the mean of that? Actually we want to make our code generic code. So let's say I want to previously my code was working for it was working for only 1 byte data. So if I am writing like 7 down to 0 or 15 down to 0, that means we are restricting our circuit for the limited bandwidth. But let's say I want to make my code generic, so I can use tick define mechanism. It is the actually tick define is nothing but a Verilog macros. So here I am defined address width is 6, data width is 32 and depth is 64, right? So let's say I want to make change in our code. I want to deal with 64-bit data address width. So I can simply here only one place I can make changes and it will automatically take everywhere. How? Let's say here I have declared data width, that is 32, and here I am writing tick data width. So what is the value of data width? It is here 32. So it will take 32 minus 1, that means 31 down to 0. Similarly address width, so here address width is 6, so it will take 6 minus 1 means 5 down to 0, right? So there will be a relation between the depth and the width. So first let me declare a memory, and after that memory declaration we will see what is the relation between address depth and what is the relation between address width and depth. So this is called memory declaration. how we can declare the memory? Just write reg, after that tick data width -1 down to 0. After that you can give any name of your memory, let's say mem. After that here tick depth -1 down to 0. That is something called memory declaration. Now we will see what is the mean of that. So let's say this is your memory, right? It may have some sections like that. Right, so this thing, and let me create some more sections. Like that. Means, let's say if I am writing something here, so actually this we can say this thing will be called the width W, right? And this thing from here to here, this thing is called depth, right? So whenever you want to declare a memory, so the syntax will be, first of all we need to declare the width, after that the memory name, let's say memory name is mem, and after that the depth, right? So that is the standard syntax how we can declare the memory. So here in our code you can see what is the depth. Depth is 64 bit, right? So it will take 64 minus 1, that is 63 down to 0, right? So that means that will be your 0th location and that will be your 63rd location, right? So now what is the relation between address width and depth? Simply means, what is the relation? So simply you can write 64 means the depth should is equal to 2 raised to the power address width, ADDR address width, right? So you can see our address width is 6, right? So 2 raised to the power 6 is 64, right? In simply let's take some simple example. So let's say this is the width, right? And I am declaring a memory like that. Means let's say 7 down to 0 mem, and here will be my width, and let's say width is 8 only, so that is also 7 down to 0. So that is 7 down to 0, it means width. So width, that means here will be your 0th bit and here will be your 7th bit, right? So in this way all data will be stored. Here will be your first, here will be your second, like that, right? And the depth is 8 bit, so here will be your 0th bit, here will be your 7th bit. So total 0 to 7 is 8. That is our depth. So how we can create the address width? So address will be, let's say you have 8 locations, right? Now you have 8 locations from 0 to 7. Total number of location is 8. So how many bit you need to access these location? That will be like 8 is equal to 2 raised to the power n. So what will be the value of n? N will become 3, right? So you need 3 bits only to access all these 8 locations. From how? From 0 0 0, after that let's say 0 0 1, after that 0 1 0, after that similarly from here to 1 1 1, right? So by a 3-bit you can access all these locations. So that is the relation between the depth and the address width, right? Now coming to again my coding part. So we have declared the memory, right? After that, always I am assuming that my design is working on the positive edge of the clock, edge of clock. After that, first of all I am checking whether it is enable or not, so I am writing if enable, right? Begin and, right? After that else. So let's say I am writing only one display, $display. Here we can write RAM is disabled, because it is, if it is not enabled, then definitely else part will print that RAM is disabled for our just for our info purpose, right? Now coming to the enabling part. So once RAM is enabled, so first of all what it will do, it will check for the reset condition. If not of RSTN, reset, right? Begin and else begin and, simply. So let me declare a for loop. So when my reset is disabled, simply, so there will be two things, means sorry, not disabled, when it is reset. So what is the purpose of reset is, in digital electronics or VLSI, the purpose of reset is, means we need to know that in which state our design output is, right? So that is the purpose. So the output will be in a known state. So let's say I am writing what is my output signal, that is data out. So data out is equal to 0, right? After that we also need to reset our memory, because we have declared memory as a reg, right? And the default value of reg is x, so we also need to reset that. So let me write a for loop for begin and we need to declare that integer over here. So we cannot declare over here int, because we are writing in Verilog and Verilog didn't support it. So we need to declare over here local variable. So here we can declare integer I, right? Now we can go for loop. So I is equal to 0. After that I is less than equal to 2 raised to the power, the double asterisk is for power, right? Tick address width, right? And after that I is equal to I plus 1, right? So what is my address width? That is 6. So 2 raised to the power 6 means from 0 to, means 2 raised to the power 6 is 64. So it will run from less than or equal to 64. So 0 to 64, that will create 65. So we need only 64. So let's remove this equal to, okay? After that, simply here I can write mem of I is equal to 0. So what it will do, let's say first time the value of the I is 0, right? So on the 0th location of memory, all bit will become 0, and in next iteration the value will become 1 due to I is equal to I plus 1. So on first location all bit will be 0. So it will work like that. After that, let's say you want to print the memory, so simply you can write $display to check whether it is reset or not. Mem is equal to %p. %p is for packed format, means in a single line it will show all the fields of a memory like an array, right? After that, now come to the else part. Here real programming will take place. So here I am writing if begin end, right? So here first of all I will check for the bit write underscore read. If this bit is high, right, So means we are performing write operation. So what it will do, mem of address will equal to data in. So what is the mean of that? Whenever my this pin write underscore read is high, so data will be there, some data in will be there, address will be there. So that address will be go to the memory address, and on that address the data will be stored here to here, right? Now coming to the else part, else begin and here that is for read operation. Obviously if that pin is not 1, that it will be low, right? Read operation, so simply write data out is equal to mem of address, right? So let's say I want to perform some read operation from a memory. So what I will do, I will provide some address, then means from which address I need to read the data. So simply that address will take place inside the memory, and data will come out to the this signal, that is data out, right? After that, because now valid data is available, so my output enable will take place over here. Output enable is high, right? It will take when the valid data is available. After that, after one clock cycle, again it will become 0, right? Means once our read operation is finished, so after in next clock cycle it will become 0. When again we will perform read operation, it will become high, and after that it will become 0, right? So guys, in this way we have written the code of our RAM, and we have done with that coding part, right? So let me save this. Now what we will do, we need to write a test bench to verify the behavior of that code. So let's say my file name is ramtb.v. So here we will write the test bench. So let me show you some block diagram. That will be your test bench, right? So simply the signal with respect to RAM and with respect to test bench are correlated. Means with respect to RAM, the output enable was the input signal, but with respect to test bench, that is the output signal, right? So test bench will tell the output, the direction of output enable should be like that. That is the actually wrong direction. It should be outside. Like this, right? So with respect to RAM, output enable is the output signal, but but with respect to test bench, that will be the input signal. Simply means, like let's say the second signal is address, so we need to tell the address RAM. So with respect to RAM, that is the input signal, and also data in is the input signal, but with respect to test bench, these signal become output signals, right? Similarly for data out, write, read, enable, right? So we need to design that the structure of the test bench, and that is something called, okay, we'll discuss later. So first of all, let's say module top and module here, output should be rest type only. Means that it is the rule of Verilog, whatever the output with respect to the module top, that or with respect to your test bench, that should be output only, right? So reg clock reset n enable, after enable one is write underscore read, they all become output, and reg type. And next one is reg, here tick data width -1 down to 0, that is data in, right? After that reg tick address width -1 down to 0, that will become address. Next one is wire tick data width -1 down to 0, that will become data out. Next one is wire, that is output underscore enable, right? So next one is reg tick data width -1 down to 0. Here we are declaring the internal memory. We will discuss later what is the purpose of that. Tick depth -1 down to 0. As similar we have declared over here in our design, right? And similarly we are declaring here. That is internal mem of TB, test bench, right? Next one is reg tick data width -1 down to 0. Okay, we may need some local signal, but we'll discuss later what is the need. So as you can see, some signals are rest type and some signal are wire type. So with respect to test bench, whatever the output we are going to generate or we are going to give to this design, that output of the test bench should be rest type only. As you can see, clock, reset, enable, write, read, data in, address, they all are rest type. But whatever we are taking from the design, means we are taking data out, so that will be wire type. We are taking output enable, that will be wire type, right? So that is the rule of the Verilog, right? After that, next one is port connection. So to connect the port, first of all just write the module name, right? Here the module name of design, right? So that is RAM. After that give some instance name, let's say DUT, and after that we can connect the port. So actually port mapping is two types. One is named based mapping, second one is position based mapping, right? So here I am doing position based mapping. So position based mapping means in the same way, in the same sequence, whatever the signal you have declared over here, in the same sequence you have to write all the signals over here, right? So first of all clock is there, so just write clock. So what is the mean of that? The clock of our test bench here, so that clock is here, so that clock is connected with the clock of the design, right? Similarly the next one is reset n, right? Now we have connected the reset. Next one is enable, after that address, after that write underscore read, after that data in, next one is data out, next one is out underscore enable, right? So let's say you have you have declared here output enable first and our data out last. Means what I am saying, let's say you have declared like that. So what happens, the output enable will connect to the data out of the design, and the signal data out will connect to the output enable of the design. That is actually wrong mapping, right? So we need to take care of all these things in position based mapping, right? Position is important. So we have done with the mapping. So now let me tell you what we have done in the block diagram. Actually these signals, right? So we have connect all these signals to each other, the test bench signal to the ramp signal. That is called port mapping. That's it. Because obviously this is my one module, this is my another module, and we want to communicate between two modules, then also means obviously we need some connections, right? Now next one is clock generation logic. How we can generate the clock? So simply just use initial, begin, end. Inside that give some value of the clock. Let's say clock is equal to 0, means I am assuming my initial value of the clock is 0, right? And after that I am writing forever #5 clock is equal to tilde clock. So means after initially the value of clock is 0, and after every 5 nanosecond I am toggling the value of the clock, right? So it will toggle the value of the clock at every 5 nanoseconds. So what will be the clock period here? Clock period will be T on plus T off. So T on is 5, means that means T on is 5 and T off is also 5. That means clock period will be 10 nanosecond, right? If you are not declaring any time scale, then automatically it will take nanoseconds, right? After that reset generation. Initial, begin, end. So before going to the resetting part, let's come here. First of all, we are not checking in the reset. First of all, we are checking whether the chip is enable or not, right? So first give the value of enable pin. So enable is 1. After that now you can go for the reset mechanism, right? So simply write RSTN is equal to 0. It is for active low reset, right? Most of time in every design, maximum time the reset is active low. #10, give some delay. And guys, if you know the reason why the reset is active low, then please comment. We'll check and we'll also respond, right? After 10 nanoseconds the value will become 1, right? So means when reset is 0 it will execute this if part, and when reset is 1 it will come to the else part over here, right? So we have done with the reset generation. Now again initial, begin, end. And here I am writing, I need to write some task, let's say write mem, means that task is responsible for write operation in the design, and give some delay, let's say has 50 nanosecond. After that I am reading, so let's say task name is read mem, right? And we also need to compare the things, means let's say my location is hex 10, right? On hex 10 location I have written the value 12. So while I am reading the value from hex 10, then it should be 12 only, right? If it is not 12, that means there is some problem in the design, right? So we also need some compare mechanism. So I am writing a task name is, let's say, comp, right? So now we need to develop all these tasks. So first of all, task write mem and task. So inside, first of all, for write operation, the value of write underscore read should be high, right? So write underscore read is equal to 1. After that, that is for write operation. After that, address. So we can give some random address. That is the good practice. So I can write address is equal to $random, right? After that, what is $random? It is actually inbuilt Verilog function responsible to generate the random values. Inbuilt function of Verilog generates the random values, right? Now after that, data in. So data in also $random means it will generate the random data. Now I need to store the value of address in a local variable. We'll see why we need. So let's say one local variable name is address underscore L is equal to address. So whatever the address this function will generate, it will also store in the local variable, right? So we need to declare the address underscore L kind of thing, right? So just declare over here local variables. Here you can write like reg tick address width -1 down to 0. That is your local address. So addr underscore L, that's it, right? After that, we have done with that part, and we also need to store the data in local memory. So temp of address underscore L should is equal to data underscore in. So what we are doing, we have generate some random address and random data, and we are sending the design, as well as we are also saving that local memory, the same thing on the same address. On the same address, the same data we are storing in a local memory. Why? Because during comparison mechanism we need that, right? Okay. So we can also write some display mechanism like $display. Here we can write let's say write packet. After that, enable is equal to %h, write underscore read is equal to %h, address is equal to %h, date underscore in is equal to %h, and here enable write underscore read address and data in, right? So we have done with the write mem task. Now we need to come to the task, that is the name is read mem. So that task is responsible for read operation, right? So simply for read operation, first of all the value of write underscore read should be 0. After that, address means from which address we need to read. So simply addr is equal to addr underscore L, means we declared here the local address, right? So on the same address we need to read the data whatever we have used previously. After that, temp, okay, not temp because we are in read operation, okay. After that, wait for output enable. means here it will wait for this value to become 1, right? 1 it is become 1, then begin end means data is available at the output. So data underscore out, let's say one local variable, that is L, is equal to data out, right? Now we also need to declare that this local variable, right? So that is the local variable declaration for data out, and after that we can write the display statement. So let's copy from here, and obviously this is my read packet, right? After that enable will be there, read write is there, address is there, and it is actually data out. Right, so that is all about our read operation. So till now we have write a task for write operation, that is the task. After that we have write a task for read operation. Okay, after that we need to write a task for comparison, that is comp, right? So task comp and task. Here I can write simply if temp is my local memory, I have declared over here at top, that is my local memory, right? If let's say begin end, if temp of address underscore L is equal to data underscore out underscore L. So I'm comparing the thing. That means if this condition is satisfied, $display, you can write RAM is passed, and $display, we can also print the value, right? So temp of percentile H is equal to percentile H, and data out underscore L is equal to percentile H, and here I can write address underscore L, temp of address underscore L, and data out underscore L. So it will print the value as well, right? After that, coming to the else part, else means if this condition is not satisfied, right? Begin end, just copy and paste. So RAM is filled, right? So we have done almost, and logic to end the simulation. Initial, begin, end. Here let's say you are writing as 1000 and $finish, right? So we have done with the coding part. Now we will execute the code and we'll see. So that is the define file, that is the top file. That is the design, and we need to include that define file also. So here tick include defines.p. tick include defines.p. That's it. Select the tool already selected and run. There is some issue in line number 53. What it is saying for this, illegal reference to net data out underscore L. Okay, we'll see. So here is the declaration of data out underscore L, right? So here we have declared it as a wire because I have copied from here, so it should not be wire, actually it is reg type only, reg. Now run this code, and also let me correct inside the file. Now guys, you can see this is the value of write packet. Enable is 1 and write underscore read is equal to 1. That means write operation. Address is 24 in hexadecimal and data in is this C0895E81, right? And it is printing memory from the design. It is showing all the fields are resetted from here, right? It is printing from here. Or you can see the field one by one. So what you can do, just delete it from here and write over here. Now run this code and see the difference. So you can see, because it is inside for loop, right? So it will print every time. You can see the iteration of for loop, how it is working. First of all the fields value were x, right? And only one value will be 0 at first iteration. On second iteration, 2 value becomes 0. After that, not values, actually locations, right? After because it is in print format, so it is actually values, right? So 1 becomes 0 in second iteration, 2 locations, 2 values become 0. After that, 3, 4, like that. You can see, right? And this total value will be total count of 0 will be 64, right? So you can see we have write a packet with this value. Address was 24 and data in was C0895E81, and while we are reading from the same location, right? Same location means address is 24, so it is giving same data. Whatever we have written on that location, we are getting the same data. That means RAM is passed, it is working properly. Also it is printing the means address inside 24 in your local memory, temporary memory, and data out is this, right? So it is working perfectly. Okay, so that is only a single write and read operation. So let me, no need for that. So if you want to perform some more iterations, so what we can do, you can simply write repeat begin and here you can give some values, let's say 10. Now run this again. So now it will generate 10 packets. So you can see first write packet value was 24, C0 this, and while it is reading the same values on the same location, so data in and data out is same. That way RAM is passed. again it is generating the, okay, it is printing from the local memory, that is totally okay. The second packet is enable 1 write read 1, address is 09 and data in is this v1 fo5663, and while I am reading, so data out is same whatever we have written over there. So you can compare always the address values, address will be same, and data in data out should be same, right? So everywhere you can check randomly. Here you can check 462D F78C 462D F78. That's why it is passed, right? Now one more thing, let's say I want to customize my design, not customize, I want to make some changes. Previously it was the single location width was 32 bit, so now let's say I need only 8 bit. One means in a single location now only 8 bit can store, right? Also let's say I want to change the depth to 8. So if total number of location is 8, then 8 is equal to 2 raised to the power n, so n will become 3, so address will become 3. Now the same code is working for this thing, right? So that is the actual benefit to use tick define, right? So your code will become generic automatically. Now you can see it is working fine. You can see the things. Address is 5 and data in was 12. While I am reading, then from address 5 the data is 12, right? I am writing 0D on address 1 and I am reading 0D from address 1. So that is working perfectly, right? So guys, this is the way how we can design and verify a RAM or a memory in Verilog style, right? So guys, if you have any doubt, you can make comments, and we'll also share the WhatsApp number in the description, right? And guys, also we are providing a training program for fresher as well as professionals, right? So can contact me through WhatsApp. I will share my number in the description box. Okay guys, thank you so much.